Welcome to my talk about emergent models, frameworks and hardware technologies for big data analytics. In my talk, I will provide an excerpt of current ongoing discussions and research in this area. Note that it can only be a short overview as the topic is too huge to fit into some hours. I hope you enjoy my selection of topics. However, first I want to introduce myself to you. My name is Sven Kroppe and I'm a senior researcher at the University of Lübeck. My qualifications are based on my career, which I started by studying computer science with minor fields physics in Paderborn. I also got my doctor degree from some time later from the same university. I earned my habilitation degree at the University of Lübeck, which is also my current affiliation. I am the lecturer of a selection of topics in the areas of semantic web, databases, information systems, compiler design, algorithms and data structures, and so on. My publication records covers over 100 peer-reviewed publications. I am the member of over 60 program committees and reviewer of over 15 journals. My other scientific services include being editor of 3 open access journals and the workshop chair of the Semantic Big Data workshop series associated at the ACM SIGMOD conferences, as well as very large Internet of Things in conjunction with VLDB 2017. Furthermore, I was a member of the ISBCC working groups which developed the RDF query language Sparkle and the semantic web rule language Riff. I hope that my activities can convince you about my qualifications. Big data experts characterize big data with words starting with a V. The most common ones are coined to Douglas Laney, which uses volume to express that big data must have some certain data quantity, with velocity to refer to an enormous speed of new data, and rarity to remember that in usually heterogeneous environments there are a lot of data types and formats to be processed. Starting with Douglas Laney's 3 big V's for characterizing big data, an increasing number of big V's occur in the scientific literature and in the web. I think all of you know it already. Some references enumerate already about 10 big V's. One of these most important big V's is the value, which refers to the data usefulness. We should be able to process today's masses of heterogeneous data in order to conclude new information, to use the data for new applications and have some benefits from them. Otherwise, handling with big data would not be meaningful for us. While the big V's only refer to qualitative characteristics, we now want to look at the quantity. An impressive comparison has been done by David Wellman. I adapted his comparison for this talk. He just lets the listener imagine that a byte consumes as much space as 1 grain of rice. So, very little space. Then kilobytes compares to a cup of rice. Megabytes consume already as much space as 8 bags of rice. Gigabytes must be then already stored in 3 semi-trucks. For terabytes, you already need 2 container ships. Petabytes then blankets already Manhattan. And exabytes blankets about half of India. So everyone from you can choose which half of India. Zettabytes fills the Pacific Ocean. and yottabytes is then already an Earth-size ball. So, how many data is processed today? Kilobytes is the area of early home computers. Actually, this one was my first computer having a capacity of 64 kilobytes. Megabytes to few terabytes can be already stored and processed by today's personal computers. Petabytes are the estimated amount of data in the traditional internet, except of e.g. modern social media platforms. And in the range of exabytes to zettabytes are big data applications, like those of today's social media platforms. And in the near future, there could be the storing and processing of yottabytes. Okay, that's today. Of course, we can also ask now the question if there is no limit of the volume of big data. So, 1 zettabytes as processed by social media companies are in the area of 10 up 21 bytes. The next step would be, as already explained, to store and process yottabytes, which are 10 up 24 bytes. So, today's disk drives use about 1 million atoms to store a single bit of information. But techniques arise to shrink the size about a factor of 6 and even 9, i.e. about 111,000 atoms per bit may be possible for future generations of hard disks. Other researchers posit that densities of 10 terabits per square inch are theoretically possible using their approach of combining thermally assisted magnetic recording and bit patterned recording, such that 11,000 atoms per bit may be possible. There are some further approaches, which currently work only in laboratory and are far away from being practically used in a data center or even anyone's computer, much more than the previously mentioned methods. For example, researchers from IBM developed a method to store 1 bit in 12 iron atoms and 1 byte in 96 iron atoms for several hours. In another approach, Kalf et al. Built a memory of 1 kilobyte, i.e. 8,000 bits, where each bit is represented by the position of one single chlorine atom. Finally, Moon et al. Describe an approach to store 35 bits per electron such that tens of bits can be stored per atom. Again, the last approaches are not practical, as the speed of reading and writing and durability are too worse. Hence, let us consider about 100,000 atoms per byte to be a realistic number for future generations of external storage technologies. So, let's look how many atoms our Earth has. So, if we additionally consider that our Earth only has about 10 up 50 atoms, then we can only store about 10 up 45 bytes in the atoms of the Earth. If we only use the atoms of the Earth's crust, then based on the estimations that the Earth's crust is only about 0.473% of Earth's mass, we can estimate that the Earth's crust contains about 6 multiplied with 10 up 47 atoms, such that we can store only 6 multiplied with 10 up 42 bytes in the atoms of the Earth's crust. So, however, we need masses of atoms for other things, not just for storing our data. Hence, we are also not so far away from a natural limit of big data, at least if we do not consider interplanetary computing, i.e. computing spanning over different planets, but this belongs also to the science fiction corner. Gordon Moore observed that the number of transistors in a dense integrated circuit doubles approximately every 2 years. His law was later adapted to other areas and describes in general the exponential growth of processing capabilities of a single computer. However, what we today recognize is that the growth of data to be processed is also somehow exponential, but growing faster than the processing capabilities. Some decades before, it was common sense to expect that the next generation of computers can handle those problems not processable by the older computers. Today, this is on the one hand still true, but on the other hand, it seems to be that today's applications and infrastructure are designed to produce as much data as possible, leading at some point to a processing demand not to be handled even by future computer generations. Furthermore, because of physical laws like those of quantum effects, the more area seems to come to a natural end, i.e. the growth of processing capabilities of a single computer may at least slow down, or even the processing capabilities do not increase at all anymore. Hence, there must be other ways to handle the big data flood. Completely new computing paradigms like quantum computing, promising exponential speed up but only for certain calculations, and neuromorphic computing modeling, processing elements on neurons in the brain, are still not far away from laboratory. The only currently feasible way seems to be using parallel computing, which requires parallel algorithms to work on partitioned data, scalable with big data flood whenever the data can be partitioned in disjoint fragments to be processed mainly independently from each other. So, one of the biggest boosts for distributed computing is dated to be around year 2000. At that time, hardware capabilities like the processor clock rate, network bandwidth, and random access memory (RAM) capacity reached the giga range. And Intel and AMD released 1 GHz processors which could be operated with 1 GB of RAM and connected with each other by gigabit Ethernet. This so-called G phenomena started the 5th development phase of computing systems. Having hardware capabilities in the giga range, a virtual integration of spatially distributed computers became plausible, leading to the grid and cloud computing paradigms, where the grid computing paradigm lays the foundation for high-performance distributed computing systems, which were evolved to scalable distributed computing systems by the cloud computing paradigm and the Internet of Things. We recognize that cloud computing is currently widely used by an increasing number of companies, which are migrating from static, centralized cluster environments to more elastic, scalable, and potentially cheaper cloud-distributed platforms. Also, small and medium-sized enterprises, as well as fast-growing startups, use clouds to react on demand on rises and falls in service demands in a more flexible way and to pay only the resources they used according to the pay-by-use business model. However, we currently observe a shift to Internet of Things applications, which require to handle much more streaming data, as well as future research problems, for example, real-time human brain simulation. Hence, the cloud computing paradigm needs to be questioned, as it may not solve, e.g., scalability challenges for these applications. Indeed, evolved computing paradigms like fog and dew computing, as well as hardware accelerators like GPUs and FPGAs, are already knocking at our door. The maximum inherent parallelism is limited. There exists a start-up and termination overhead for each computing node. Different nodes may interfere during the access to the same physical and logical resources. Some nodes may be overloaded. There may be log conflicts, skew in the execution times of subtasks, the partitioning of jobs and data may not be scalable, and so on. Hence, a linear improvement in the speed up according to the number of used nodes is typically not achievable. Experiments show that the speed up usually does not grow after a certain optimal number of nodes, and often decreases behind that optimal number. Based on these observations, Amdahl concluded in his law that if the parallel algorithm has a fraction of a sequential part, as it is typically the case, then the speed up is limited. For example, only a 5% sequential fraction of the overall algorithm leads to a maximum speed up of 20. A higher speed up is theoretically not reachable. Indeed, this sounds very pessimistic. But there are also optimistic considerations. Gustafsson wanted to overcome the shortcomings of Amdahl's law, which only considers speed-up improvements for fixed problem size and fixed input data size. He argued that programmers tend to set the size of problems to fully exploit the computing power that becomes available as the resources improve. He concludes that if faster equipment or more nodes are available, larger problems can be solved within the same time. Hence, he fixed the execution time and looked at how much larger the problem size or input data size can be while running the same algorithm on more nodes within the same time. This way of thinking fits much better to our future big data problems. We will now take a closer look at the current available big data analytics engines. Just looking at the big data landscape from Matt Turk, I get the feeling that you can't really name me a big data expert. There are so many views on big data, so many systems, applications and tools. To be honest, I only know a small fraction of them. And of course, the figure does not contain all of the big data landscape. Maybe some of you already discussing what is missing inside. In other words, if you discuss with someone else about big data, you must know her or his background context in order to get an idea about her or his big data and put it into relation to your understanding of big data. At least this is what I experienced so far. So, what is your accept of big data? In the following slides, I will dive into some details and compare different platforms for big data analytics engines. especially in terms of data and query processing on big data. But be aware, there are so many frameworks outside such that not all will survive. It becomes very important to choose the right technology to surely handle the big data flood, but also to choose a future-proof framework, the development of which is going on in the future and not becoming inactive after some time, because maybe another framework is more popular or offers a better background technology. Currently, the systems do not seem to evolve, and new approaches and technologies are integrated only in a newly developed system. Or in other words, there seems to be two floods. One is about the explosion of generated data to be meaningfully processed. The other flood contains upcoming new frameworks to handle this big data flood. The typical big data analytics stack includes a layer for the data and the access to it. Engines for big data analytics usually provide access to data in databases, in distributed storages or streams. Engines especially deal with distributed resource management and distributed execution. They provide the capabilities to application developers and big data experts in terms of an application programming interface (API), and often by supporting a high-level scripting language and even SQL-like query languages. Big data engines often have specialized APIs for processing streams, applying machine learning and graph processing applications. Big data engine developers make huge efforts to integrate the product into the existing big data landscape and reuse a lot of the existing technologies for import and export of data and the processing results. However, some core modules, like the APIs for data, stream and graph processing and machine learning, as well as scripting and query languages, are often reinvented, such that there is also a big migration effort necessary for changing an underlying big data analytics engine in an existing application. Let us look at the evolution of big data analytics engines. While the original Hadoop version 1 system introduces the map-reduce programming paradigm with a focus on batch processing of big data with applications e.g. in targeted advertisement and log analysis. The next generation of engines already supported enough performance for user interactivity. TEDS hence also extended the processing model to allow directed acyclic graphs for the data flow between different processing units. The third generation, to which Spark belongs, already supports near real-time and iterative processing by handling mini-batches and introducing resilient distributed datasets, enabling in-memory computations on large clusters in a fault-tolerant manner. Apache Flink is one engine of the current fourth generation, which supports real-time processing of streams by native iterative processing instead of internal mini-batch processing as in Spark. The processing model of Flink also supports cyclic data flows. So the interesting question is now, seeing at this all What will be the key features of the next generation? So, I also don't know, but I will try to speculate in the following about this issue. Possible directions for the fifth generation of big data analytics engines might be the support of coprocessors. There are already some few research efforts to use GPUs and FPGAs in Spark. But these systems seem to be preliminary. Another direction could be to integrate the use of smart SSDs into the engines, such that data is already filtered at the SSD using the processing capabilities of smart SSDs in order to drastically reduce transfer costs between the SSD and the memory of a cluster node. There might be also tendencies to go away from cloud computing as the transfer to nodes are bottlenecks, especially for Internet of Things scenarios, such that processing capabilities closer to the sources of data generation are used instead or complementary. Approaches like fog and queue computing may be adapted for future generations of big data analytics engines. We try to shed lights on these emergent hardware technologies and computing paradigms for the usage in big data analytics engines on the following slides. General Purpose Graphics Processing Units, GPGPUs, turn the massive computational power of a modern graphics accelerator shader pipeline into general purpose computing power. Although graphics processing units, GPUs, are not necessarily meant for general purpose computing, GPGPUs and GPUs are often used synonymously. And so we will just use GPU in the following. GPUs basically work according to the single instruction multiple data paradigm, where the same instruction is executed on different data on different cores at the same time, i.e. not all parallel algorithms are suitable for GPUs. Modern GPUs offer several thousand computing cores, such that some applications are greatly speeded up in comparison to multi-core CPUs. There exists a lot of proprietary and also vector-independent programming standards for programming GPUs. The most important one is OpenCL. Field Programmable Gate Arrays, FPGAs, contain an array of programmable logic blocks and a hierarchy of reconfigurable interconnects that allow the blocks to be wired together. Logic blocks can be configured to perform complex combinational functions or merely simple logic gates like AND and XOR. The FPGA configuration is typically specified by using a hardware description language, HDL. In comparison to software development, developing HDL programs is often more than 6 times slower and more error-prone. So you must know this before you start developing for FPGAs. It needs very often much more time. Recently, high-level synthesis, e.g. OpenCL, is more nature, such that the development efforts of FPGA programs becomes comparable to software development, but still performance-critical parts should not be implemented in OpenCL, as they have a high overhead. Furthermore, although OpenCL programs developed for GPUs are also running on FPGAs, they need to be optimized for FPGAs to avoid worse performance and achieve better results with FPGAs. A main disadvantage of FPGAs is that it takes a very long time from an HTL or OpenCL program to running the configuration on the FPGA. Often developers need to wait hours for this process. So there is no problem if the FPGA should run only one configuration. However, if the FPGA should be reconfigured during runtime, there are some tricks for an efficient procedure necessary. There are also different types of FPGAs. The most widespread platforms are PCI-attached FPGA acceleration cards to be hosted by a normal computer. These systems have the disadvantage that there are additional communication costs over the PCI bus. Your design of your approach must hence take care that the overhead of PCI communication cost does not outweigh the benefits of applying FPGAs. Often you can mask this overhead by pipeline processing and transferring not too small blocks over data over PCI, but still there might be some latency problems. Shared memory systems, on the other hand, enable FPGAs to access the normal DDR-RAM of the host computer in the same way as the CPU can do. Some shared memory systems even support cache coherency between CPU and FPGA. These systems do not have additional communication costs and avoid latencies. Furthermore, the CPU and FPGA can even work on the same portion of data in parallel, and hence distribute tasks between them in a more flexible way. Note that also GPU acceleration needs expensive PCI communication, such that shared memory systems have considerable advantages over GPU acceleration too. Some selected researchers can access such a kind of shared memory system as participants in the Intel Hardware Accelerator research program. Our research group is also a participant in HARP. There are also multi-FPGA systems available, where several FPGAs are connected with each other and with the host computer, often via PCI bus. Multi-FPGA systems allow scalable FPGA solutions, which have higher demands than one FPGA can provide. We will compare multi-core CPUs, many-core CPUs, GPUs and FPGAs with each other. In a simplified schematic view of the parallel architectures, we can divide the components of the architecture in computational units, execution controllers, interconnection network, and on-chip memory. Today's multi-core CPUs have shared memory for all cores, but each core owns own memory, typically fast memory in form of caches, its own execution controller, and a computational unit. Hence, multi-core CPUs are suitable for applications that benefit from high single-core performance, scale only moderately, run threads with different functionality according to the multiple instruction, multiple data paradigm, are control flow dominated, rely on shared memory, and access memory only in irregular patterns, which benefits from caches. Many-core CPUs manage now much more cores, but the architecture remains similar to the one of the multi-core CPU. However, many-core CPUs are optimized for a higher degree of explicit parallelism and often for higher throughput at the expense of latency and lower single-thread performance. Hence, many core CPUs are suitable for applications that scale well, have threads with different control flows, and compute mostly on private data, with sometimes access to some shared data. A special type of many-core CPUs are graphics processing units, GPUs, suitable for vector processing evaluating the same instruction on multiple data in different cores. Groups of cores typically share some faster memories, most often used as caches of the global memory. GPUs are hence suitable for applications that utilize data parallelism, run threads with identical control flow, access memory in regular patterns, work on small static working sets without dynamic memory allocation, and use floating point arithmetic. Field Programmable Gate Arrays (FPGA) are special because the interconnection network between its cores can be configured, making them ideally suitable for data flow-driven algorithms, as well as fast on-chip memory is massively distributed and hence can be accessed in parallel by its numerous cores. So, hence, FPGAs are suitable for applications that are designed in a data flow style by implementing processing pipelines and process streams of data. So, this slide and the following is also adapted from a talk from Plessel. I don't want to hide this. We can further characterize the different parallel computing architectures in the following way. Multi-core CPUs have few but complex cores, optimized for single-thread performance, ideal also for sequential programs. The number of cores for many-core CPUs range in the area of hundreds, whereas GPUs can have several thousand cores and FPGAs specialized in simple several 100,000 cores. The computational model varies from multiple instruction, multiple data for multi-core CPUs over single instruction, multiple data for many-core CPUs and GPUs to data flow driven in the FPGA case, having thread parallelism over data parallelism to an arbitrary parallelism of FPGAs, because the interconnection network as well as computational units can be configured in an arbitrary way. We now compare the different architectures concerning performance in terms of integer and floating point operations per second, ease of coding, flexibility of usage, suitable for hard real time, and the operations per watt. The multi-core CPU is known to be very flexible and hence easy to program, but is not very efficient, as only few cores are viable for parallel programs and consumes much electric power. GPUs are highly parallel and hence have a better performance by slightly reduced flexibilities, but they consume less electric power. FPGAs are still fully flexible, having a better integer performance by reduced consumption of electric power by a factor of about 10 in comparison to CPU, GPU systems according to some recent studies, but are very difficult to program. So the situation about the ease of coding is currently changing with the support of OpenCL. But still FPGA providers state that at least performance critical parts should not be implemented with high-level synthesis like OpenCL or C++. Application-specific integrated circuits, ASICs, are not flexible at all, as ASICs are integrated circuits, ICs, customized for a particular use. Hence the ease of coding is somehow comparable to FPGAs, but the performance can be much faster by consuming less electric power by a factor of about 7 in comparison to FPGAs according to some recent studies. So, looking at this all, we can now look at if there are some benefits in practice. So, it is time to show some concrete results of our research group. In our research group, we developed the semantic web database LupoState. I will give some more details about LupoState later in this talk. We investigated also hardware isolation of semantic web queries as an extension to the LupoState system. We developed a system to quickly exchange the FPGA configuration for new queries to be executed by using dynamic partition reconfiguration of the FPGA. Such as in traditional database systems, our hybrid system needs to be deployed before using it for query processing. Alongside the obligatory installation of the mandatory software and initial import of data, the static logic has to be deployed on the FPGA, and the reconfigurable modules for all possible operators to be executed on the FPGA need to be generated and stored in the repository. After the hybrid system has been deployed, the user can submit a query which is transformed into an operator graph by the LupoState system. On the operator graph, several logical and physical optimizations are applied. Afterwards, the optimized operator graph is analyzed for unsupported operators of our hybrid system. If all operators are supported by the FPGA implementation, then our new extension traverses the operator graph and chooses appropriate reconfigurable modules in terms of operator type. The chosen reconfigurable modules are configured, setting the final structure of the operator graph on the FPGA. The operator graph can then be executed on the FPGA by transferring the tuples to the FPGA and the results of the FPGA processing back to the host system. Yeah. Just to mention, if an operator graph is not supported by our system, or if there are any other errors, we can fall back to the pure software system and process the query just in software. The software system can be also used in parallel if the FPGA solution is currently overloaded. In order to reconfigure very quickly, we must hence hold a static structure of an operator graph on the FPGA. Any operator graph of a query to be processed must fit into this static structure. Otherwise, we must fall back to the software system. However, in this way, only small parts of the FPGA need to be reconfigured by pre-processed configurations. We reconfigure the spaces left for the operator logic in the semi-static operator graph, as well as the routing elements for connecting the operators in the operator graph. The results are quite remarkable. The time needed for reconfiguration has been reduced from about half hour to few milliseconds. In more detail, less than 20 milliseconds for all queries, when using semi-static operator graphs in comparison to a solution without dynamic reconfiguration. We achieved speed-ups between 4 and 32 for datasets with several 100 million tuples, which is an enormous move for query processing. These results are quite promising, such that we should think about an integration of similar systems into big data analytics engines. We envision a tight integration into the APIs of big data analytics engines like Spark and Flink, such that it is possible to run the big data analysis in software or on FPGA, depending on which hardware is available, is currently overloaded, and so on. Note that the experimental results are also done only on one computer. So, if we have several computers, all having FPGAs and so on, the results might be much better. Furthermore, the results are obtained by PCI-attached FPGAs. If we now use shared memory systems for FPGAs, then the latencies for PCI communication will be also away. So the results will be also much better. While assimilation by coprocessor like GPU and FPGA are suitable as extensions to today's computing infrastructure, which have a central gateway like it is the case for cloud computing, we want now to shortly discuss other emergent computing paradigms here. For this purpose, we first found out the problems of cloud computing in context of new application scenarios and contexts like the one of the Internet of Things. In the Internet of Things, many small devices produce a lot of sensor data and other data. Just let us consider the smart home scenario, where your things at home can be accessed via Internet, and maybe high-level applications need to process all the generated sensor data in real time. Today's solutions typically just use a cloud to collect and store all the sensor data and other data of your things. However, the connection from your things to the cloud is a bottleneck, as these data must be continuously transferred over wide area networks. It is also not a scalable solution, as the problem of the bottleneck becomes bigger for more things at your home. Furthermore, the transferred data may contain sensible data like exact times of your presence at home. Hence, there's a security risk for you, as the data may be misused by the company, by criminals within the company, or criminals hacking the company's computing infrastructure. The fog computing paradigm, on the other side, is mainly coined to Cisco systems. There are also other names for the same paradigm, like edge computing. Fog computing utilizes near-things edge devices with higher capabilities to carry out a substantial amount of storage, rather than stored primarily in cloud data centers. Communication, rather than routed over the internet backbone and application logic. Hence, the main advantage is that the data resides at owner's infrastructure, which reduces the discussed security risks of cloud computing. However, fog computing is not really scalable in the number of connected things, as the near things edge devices do not increase in number and capabilities in the same way. Hence, there are ideas collected under the two computing paradigm, which also utilize the things themselves for storing, processing, and management tasks according to the observation that their capabilities also steadily increase. So, in two computing, the near things edge devices are still used as before. Additionally, now the things themselves fulfill tasks of the high-level application and store the raw data and its processed results. The advantage remains that security risks are reduced compared to cloud computing, as the data resides at owner's infrastructure. Furthermore, queue computing is really scalable with the number of things. As more things are there and produce data, as more things also offer the capabilities for storing and processing. So disadvantages are, besides problems of heterogeneous and environments in general, that the poor availability of some things needs to be compensated, which leads to further redundancies. And small things typically have limited storing and computing capabilities, such that the overall system must take care about the properties of each thing too. Our semantic web framework Lupostate already supports peer-to-peer networks as data source, which is a reasonable communication infrastructure for Internet of Things environments. However, extended research is necessary to address a lot of open questions concerning fog and queue computing. Furthermore, a tight integration of fog and queue computing into the APIs of big data analytics engines, like those of Apache Spark and Flink, might be a next step for future generations of big data analytics engines, supporting Internet of Things environments especially. So, coming back to the big V's of big data, we recognize that all the previous efforts only addressed volume, velocity, and maybe rarity by supporting various accesses to data in a flexible way. Hence, we can process any data with our current and future big data analytics engines. However, to create value is completely left to the applications of big data in the moment. We hence recognize that we need a data model which supports the creation of value out from heterogeneous data in order to decrease application development costs. Having in mind that the growth of data is today exponential, we must take care that the value of the data and the value of the result of data processing also scales with this exponential growth. Hence, there are some efforts to support scalable value already in the data model. One of these efforts is the semantic web. The current World Wide Web enables an easy, instant access to a vast amount of online information. However, the content in the web is typically for human consumption and is not tailored for machine processing. The semantic web is hence intended to establish a machine-understandable web and is also currently used in many other domains and not only in the web. For this purpose, the semantic web uses especially ontologies as additional abstraction layer, which have considerable advantages over schema descriptions. In this additional abstraction layer, background knowledge can be specified, based on which new facts can be derived, which avoids redundant information, supports reuse of data and data integration, but increases computational complexity. The ISBCC specified a lot of new languages for the semantic web. The recommended data format is the Resource Description Framework, in short RDF. The basic elements of RDF are tuples and an RDF dataset, called RDF graph, consists of a set of tuples. Hence the structure of the data is quite simple, which can be utilized for optimizations. The corresponding RDF query language is Sparkle, which basic element is a tuple pattern, with which can easily specify restrictions for matching triples. Simple ontologies, mainly addressing class hierarchies and domains and ranges of relations, can be expressed in RDF schema. Or RDFS for short, while complex queries can be formulated in OL, currently in version 2. The ISBCC also specified a semantic web rule language, which was originally meant as rule interchange format, in short RIF, which is also the name of the rule language. There are some cross-relations of the languages, i.e. the inferences of big fragment of OL, the OL to rule fragment, can be expressed by RIF rules. The ISBCC also specified the results of Sparkle languages on top of ontologies, as well as RIF inference. The semantic web layer cake was first introduced by Timur Berners-Lee in 2001. In his first version, Sparkle, OL and RIF were still missing, because they were not specified so far at that time. Semantic web layer cakes are loved by the semantic web community. Some really baked real cakes in form of the semantic web layer cake. In this version, already OL occurred as ontology language. Furthermore, the semantic web rule language, SWIL, is mentioned as rule language, which is a proprietary but successful rule language. Then in 2006, the ISBCC published an official semantic web layer cake, the core of which we already discussed in the previous slide. An interesting point is that RDF is here attributed with data interchange. Before that date, the ISBCC still proposed XML as data interchange format. As in the other semantic web layer cakes, there are some components still left for future work, i.e. the unifying logic, proof, trust and cryptographic protocols and approaches still need to be specified by the ISBCC. In 2011, Benjamin Novak wanted to blame all those who create layer cakes, because there was and still is a flood of layer cakes for all purposes in many projects. For his persiflage, he created a three-dimensional version of the semantic web layer cake to be superior to two-dimensional layer cake versions. Besides the specification and solutions dimension, he introduced the concepts and abstractions dimension. Although it was meant as persiflage, a lot of people took over his variant because they liked the additional dimension which relates the specifications and solutions to the concepts and abstractions. And although he deleted this version from his blog, a lot of people still use it in their presentations, like me now. There are already some assumptions integrated into the data model of the semantic web, which makes it ideally suitable for big data applications. One assumption is the one of the open world. This assumption assumes to have incomplete information, which is typical for real-world datasets, especially if these real-world datasets are very large, which hinders a careful maintenance, and or if they are based on qualls of data from different sources. The open world assumption now considers the truth value of a statement to be true if it is contained in or can be inferred from the given data. The truth value of a statement is considered to be false if this is directly contained in or can be inferred from the given data. All other cases are assumed to be unknown, i.e., if a statement is neither contained in nor can be inferred from the data. The opposite assumption, the so-called closed world assumption, assumes in this case the truth value to be false, as the closed world assumption assumes complete information. The database contains everything, and anything not contained in the database is supposed to be false. However, complete information can only very seldom assumed. Especially in the case of big data, they are in fact large data sets, but the way of collecting these large data sets is based on an incomplete qual or sensor logging in many times. Hence, I claim that big data applications are often based on incomplete information. Or in other words, big data applications often try to reach complete information by collecting as much data as they can. But they will never reach complete information. From my perspective, is an increasing amount of data, like it is the case for big data, a sign of incompleteness, as otherwise the data set size will not grow anymore after reaching the completeness. For example, a data source may contain that a flight exists at 2 p.m. and another one at 3 p.m. If we query for a flight at 5 p.m., then the answer is according to the closed world assumption, no, because there exists no entry in the data source about a flight at 5 p.m. So, no flight at 5 p.m. However, the answer according to the open world assumption is unknown, because it is not explicitly stated that there is no flight at 5 p.m. in the data source. There could be another data source, i.e. from another airline company, which could contain the statement about a flight at 5 p.m. The other data source is maybe currently not available or has not been found so far. Hence, in an open environment like the web, or if we know that our datasets are not complete, like it is often the case for big data, then the open world assumption makes sense, and the closed world assumption doesn't make sense. Another assumption aims at considering the uniqueness of names. In relational database theory, the names are called keys, which refer to their uniqueness, i.e. one thing, or tuple in a relation, is uniquely identified by its key. Two different keys are hence not allowed to refer to the same thing, or tuple in a relation. However, in big data, as well as in the web, often different datasets from different data sources are combined. because these data sets are typically created and maintained independently from each other, it might occur that different names are indeed used for the same thing, entity. The unique name assumption does not assume a unique name, and hence considers the possibility that two or more names refer to the same thing, entity. In our example, we have an instance Mary of type person. Furthermore, Mary has the parents Jontio, Lisatio, and Lisa Minnelli. Based on the assumption that the person has at most two parents, and considering the no unique name assumption, Jontio, Lisatio, and Lisa Minnelli are maybe not all different persons. Hence, we can conclude that two of the persons are the same, or all persons are one person. Even this possibility might be there. Looking at this, actually for humans, there's only one possibility left which seems to be reasonable because of the similarity of the given names. Having our background knowledge in mind, which we learned from our toddle age on, we assume that Lisatio and Lisa Minnelli are the same persons. Lisa Minnelli may have married Jontio in the past and took over his family name, such that she is now called Lisatio. The information of Lisa Minnelli may occur in some historic data, which might have been not updated so far, or because Lisa Minnelli was the right name of Lisa in the past, such that the statements about historic events should contain Lisa Minnelli instead of Lisatio. Calling her already Lisatio in the past, that would not be right, you see. We see that having a unique name is often very difficult or even impossible to reach, especially for big data scenarios, where several probably independent data sources contribute to the used data set of the applications. Just another remark. Of course, the example would also work if John would have taken over the family name of Lisa, or even if we use some double family names and so on. The computer needs some more information in order to have a chance to automatically conclude that Lisa Minnelli and Lisatio are the same persons. If the dataset further contains that Jontio is male, Lisa Minnelli and Lisatio are female, and female persons are disjoint from male persons, then the given first possibility can be automatically concluded. This kind of background knowledge, again, can be formulated in ontologies. And the semantic web offers this ontology technology for this purpose. The semantic web community, and especially those organized in the Linking Open Data, in short LOD, project, maintain a big data collection of freely available and accessible large-scale datasets, currently containing approximately 150 billion triples in over 2,800 datasets, as well as links of equivalent entities between these datasets. The last is very important. The central dataset of LOD is the DBpedia dataset, which is an RDF export of Wikipedia, the well-known free online encyclopedia, which has been created and edited by volunteers around the world in many different languages. So here we see an example of the data extracted from Wikipedia to DBpedia in comparison to the information presented on Wikipedia. It is only an extract of the data of Amsterdam, but this example may have already provided you hints about the large knowledge graph given by DBpedia. Because the semantic web applies the no unique name assumption, and because there are many datasets integrated in the linking open data project, they also collect links between these datasets by collecting the names of identical entities. There is the ontology construct all same as in order to declare two or more names for identical entities. The presented example contains some links for the DBpedia entity for Amsterdam and the entity in the GeoNames dataset. Please note that the links are typically given from one dataset to the other and vice versa, i.e., for each dataset the links to the other datasets are collected. Here we see the great benefit for the collection of these links. By knowing equivalent entities in two or more datasets, we can combine the data for these entities, resulting in more information about an entity like Amsterdam in comparison to just considering the data of only one dataset. The explosion of the LOD big data collection is visualized in the linking open data cloud diagram. In this diagram, each dataset is represented by a circle. As bigger the circle is, as bigger the corresponding dataset is. Links between datasets are drawn by arrows between the circles of the linked datasets. Again, more links are represented by bigger arrows. Having the most links to and from other datasets, DBpedia is the central dataset in the LOD. The LOD started with only few but important datasets, as this cloud diagram dated to March 2008 showed. 1 year later, the number of datasets and links already more than doubled. In this diagram, the colors already characterize the datasets according to different topics. In 2010, the LOD cloud already contained 203 datasets with 25 billion tuples and 395 million links between these datasets. 1 year later, 92 datasets are added to the LOD cloud, which contain now 6 billion more tuples and 109 million more links in comparison to last year. In August 2014, the LOD cloud included about 570 datasets. And this is the picture of the current LOD cloud in January 2017. I think the development and growth of the included datasets and overall size of the LOD cloud is quite impressive to all of us and shows the need for future enhancement of big data analytics engines. I guess that we need to go on with discussions and research on advanced methods and approaches to handle this flood of data, as otherwise our developed engines will think not able to handle such amount of future datasets. So, in our research group, we developed LupoState, which is an open source semantic web database supporting different types of indices for large-scale disk-based datasets and for medium-scale memory-based datasets, as well as processing of possibly infinite data streams. LupoState supports the RDF query language SPARQL 1.1, the rule language RIFBLD, the ontology languages RDFS and All2Rule, parts of GeoSPARQL and SDSPARQL, visual editing of SPARQL queries, RIF rules and RDF data, and visual representations of query execution plans, i.e. operator graphs, optimization and evaluation steps, and abstract syntax trees of past queries and rules. I would say the advantages of LupoState are the easy way of extending LupoState. Its flexibility in configuration, e.g. for index structures, integration of different data sources, using or not using a dictionary, and it is open source. These advantages make LupoState best suited for any extensions for scientific research. Hence, LupoState is already extended for Internet of Things scenarios by supporting dual computing utilizing a peer-to-peer network spanning over the things for data storage and processing. Also, traditional cloud computing environments can be utilized by LupoState in the extension pLupoState, which uses Big Latin to process Sparkle queries and optimizes query processing by an advanced Bloom filter approach. There are a lot more results obtained with the LupoState framework. For example, we already discussed the results concerning the hardware isolation via FPGAs earlier in this talk. We will take the experiences we made during the development of LupoState and the LupoState framework as well as starting point for future research in advanced big data analytics engines. So that's our plan for our research group. Summarizing all, we observe an increasing speed in the growth of the big data flood, which shows the limits of state-of-the-art big data analytics engines in the near future. Hence, we start a discussion about possible future development phases of big data analytics engines. For this purpose, we look at the integration of emergent hardware technologies like GPUs and FPGAs as coprocessors for big data analytics engines. Moreover, we discuss new computing paradigms, like the ones of fog and dew computing, which may be also utilized for future generations of big data analytics engines. We also take a short look at the semantic web, the data model of which supports mechanisms to increase the value of big data. I want to take the opportunity to make some advertisement for my current activities. Please submit papers to my workshops. The Semantic Big Data Workshop Series in conjunction with the ACM SIGMOD conferences regularly have deadlines in the beginning of the year. The Very Large Internet of Things workshop are in conjunction of VLDB conferences. The next workshop of Very Large Internet of Things has a deadline of the 3rd April 2017 for paper submission. Please check out the deadlines for future workshops. You may also submit papers to those open access journals where I'm editor. These are namely the Open Journal of Databases, the Open Journal of Semantic Web, and the Open Journal of Web Technologies. All are published by RONPUB. Thank you for your attention.